Okay, so what I'm going to do is I'm going to go through chapter 8. So what we've done on the board is we've derived everything that we've wanted for two-dimensional elements in the concept, so we understand all the concepts very clearly. What I just want to do now is to just step through chapter 8 and just go and see what is the 4-node quadrilateral, bounce of what we expect to see off it, because that's the only one that's done in detail in the book, and then also just go back to the 8-node quadrilateral and just have a quick observation or two of what's going on there. So two-dimensional isoperimetric elements, numerical integration. So the 4-node quadrilateral, first off, what we would expect to see is it's got 4 nodes, that's given, 2 degrees of freedom per node, so the element degrees of freedom is 8. And we can see here, there it's 8. That is all expected as expected, okay? We know that essentially we have now displacement U field and V field. This is essentially what we have see here. So there's the bold U indicated as a vector. U is a function of x and y, V is a function of x and y. But for, x and y is each a function of sine, eta, and tan. Let's see how that is a function of sine, eta. So for the Q8 element here, we can see Q1, Q2, Q3, Q4, Q5, Q6, Q7, Q8. There we see that. Here we can have essentially any point x, y will also have a displacement uv. That's given by the, essentially that will be given by the shape functions, a field over that element. That's important to understand. Okay, so that is just in bulk what the 4-node quadrilateral element is about. There's any kind of arbitrary shape of this will get mapped to this kind of ideal world, this -1, 1 world, yeah, in the psi eta world. So you can see psi and eta, the two variables there. Now any point P is also related to psi and eta at a point there. Okay, that's the beauty of that. And now we can say, fantastic. You can go and derive the shape functions yourself now. You understand exactly what's going on. But just quickly, let's just do N1 conceptually, just to make sure that we bounce it off. If I'm here, there must be 1 here, and the other ones must be 0. So here's one root, 1 minus eta. So eta equals to 1 is one root. So I can write it as 1 minus eta as the one root, and the other one is 1 minus psi, and 1 is the one root. Sorry, not eta. 1 minus psi is the one root, and then this is eta equals to 1. So 1 minus eta is the other root. So I can write it as 1 minus psi and 1 minus eta. And then if I evaluate it at -1, 1, I get 1 minus 2 is 2, and this is also 2, it's 4. So divided by 4 here, I will get this to evaluate to 1 at that node. Beautiful. So there's N1, N2, N3, N4, etc. We can see all of those. Okay, then essentially I have the U field, U and V fields. I can write it now as those degrees of freedom. So I can see here again, just to highlight, all the odd ones are horizontal displacement. All the even ones are related to the vertical displacement. Can you see that? So what I can see here is I can just say N1 times Q1, N2 times Q3, N3 times Q5, N4 times Q7, and then similarly for V, all the even ones will multiply with the N1 to N4. And we can write this in this matrix, 2 by 8 matrix that we saw, because there's now an Q8, 8 elements in this from 1 to 8. And so essentially we see this, all the odd terms will multiply with the respective things, and all the even terms will multiply with the respective shape functions. Beautiful. Now we can also say we can similarly write down our shape functions for x. It's a function of our nodal coordinates, our mesh that we've put down. So this is x1, y1, x2, y2, x3, y3, x4, y4. We can write that down as well. Now we have the description for x and y. N1 to N4 multiplied with the x1s, N1 to N4 summed multiplied with the respective y1 to y4. So that's beautiful. Now we have that. Here's the derivation that we did for the essentially for how things change. So derivatives, how they would relate changes in the x to changes in the psi. So if you have any kind of arbitrary function, we in the derivation of the board we did u, the function u is a function of x and y, in each one in turn is a function of psi and eta. That was quite beautiful. That worked out nicely. But yes, just if you want to do that derivation in general, then we can write it as this derivatives, the derivatives to the local coordinates is equal to the Jacobian derivatives multiplied by the global coordinates. And if you want to get the derivatives with respect to the global coordinates, we can just do the inverse Jacobian multiplied by the local coordinates. And so this is sort of standard second year maths. You've done this quite extensively, this Jacobian stuff. So this is actually quite stock standard. And then the last thing that we did not derive specifically, but the relationship between dx dy is just the determinant of the Jacobian d psi times d eta. So that's essentially just that. If you look at the Jacobian here, what it boils down to is essentially the determinant of the Jacobian essentially this times this minus this times this. Okay, so that's essentially what that boils down to. Okay, so that's like I say, the Jacobian stuff. That's sort of stuff that you can just go and polish back on your second year maths if you feel like you want to do that. But this is not so much necessary. This is really just conceptually. I want to make sure you understand where this comes from, and the derivation would be so would make it so clear that we don't have to stress too much about all the details about this. This is really just to make sure we can follow, and when you read up the manual or a textbook, that these things are not intimidating. That they really understand. This is actually conceptually, I completely follow what goes on. And if you lose track, always go back to the 1D and just conceptually ask what these terms were. And the 1D is just things are a little bit quicker to go through and a little bit more simpler to think about. Okay, so then essentially I can go and say element stiffness matrix. We need to get a description for our strain. So this is essentially derivatives of UV with respect to x, y, and y and x. So that's essentially what the terms that we require. We've derived this already now. We see that, so this is just the inverse Jacobian. This whole thing is just the inverse Jacobian. So that's all fine. We can essentially write an A matrix that takes the, multiplies with this 4x1 vector to get stuff in the right place. And we see here, what we have here is we have a 1 over the determinant of the Jacobian, and then if I look at the u dx, I see it's a j22 that multiplies by this minus j12 that multiplies by that. So if I look at this vector here, I just have to say it's u psi and eta that I need. So u psi and u eta that I need, and I just have to put in the right terms of the Jacobian. So that's those two terms. So now those two terms multiply by that. That's what I see here. That is the u dx is equal to that. This times this. I can also see that du dy is equal to those two terms multiplied by this. So du dy needs to be the, so where's this strain measure that we have? Yeah, the strain should be essentially this, du dy. Let's do, so the du dy is it's going to feature in the, let's do du dy, it's going to feature as the in the shear component. So the du dy is going to feature in the shear component, and you can see that part of the Jacobian there, which multiplies by this, is the du dy, and that's that, those two terms that will multiply by that 4x1 vector. So that's the shear contribution, the u dy, and this is the dv dx shear contribution. You can see that dv dx is the shear contribution that goes into the matrix there. And if lastly, if you look at this mid-side one, which is this third row, that's the strain in the y direction, so it's dv dy. So dv dy, it's essentially, dv dy is this 2 times this. So I get this contribution there. You can see those two terms, this row will multiply by this to give me this, and that's those two terms that will multiply by this 4x1. Everything's hunky-dory. Okay, because in this 4x1, these two terms are there at the bottom. So this is why it's the last two columns. These last two columns that we see here. Okay, because this third column will multiply with this third index will multiply with the third column. This fourth component will multiply with the fourth column. Beautiful. Now we see where the A comes from. Now we need to understand what this is all about. So this is just derivatives of the shape function of sin eta. So we can write this as GQ. So the Q multiplies by the derivatives of the shape functions with respect to sin eta. This is essentially what this G looks like for this Q4 element. Okay. So it's just really, none of this is difficult. It's just following the complexity. So it's not difficult, but it's complex. What I mean is you just have to make sure you follow the complexity of what needs to be in the right place. But all of these things, you know exactly what it's about. And then we can write it as epsilon BQ, where B is now A times G. Okay. Stress dBQ. And then once I have that, I can now write out my stiffness matrix, determine the Jacobian that relates now the dx dy into the local coordinates derivatives in the -1, 1 domain, constant thickness. If the thickness is not a function of sin eta and it's just constant, it gets pulled out in front. Beautiful.